Hello, this is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is Module 8, working with multiple random variables. So in this module, we're going to discuss a whole range of topics that are related to working with jointly distributed random variables, multiple random variables. And the first thing I want to talk about is the concept of covariance and correlation coefficient. So a number of times in this course already, we've talked about, having two random variables that are coupled in some way or have some statistical similarity. So when the output of one is large, the output of the other one tends to be large as well. And so covariance and correlation coefficient are two metrics that are used to basically quantify the statistical influence that two random variables have over one another. And covariance is defined first. It's the expected value of the random variable x minus its mean multiplied by the random variable y minus its mean. If you expand out these brackets, this is the more common form for covariance. And basically, as we're going to see, covariance, if the two random variables are independent, covariance is 0, right? So if there's no statistical influence between them, the covariance is 0. If there is a statistical coupling between the two random variables, then covariance is non-zero. It gets larger. A closely related metric is correlation coefficient, which is basically just normalized covariance. So it's the covariance divided by the standard deviation of the x random variable and y random variable. And since the absolute value of covariance has to be less than or equal to the product of the standard deviations for x and y, the correlation coefficient, or that should be the magnitude of the correlation coefficient, is less than or equal to 1. Correlation coefficient is actually perhaps the quantity that we work with more because it has maybe more intuitive meaning. So correlation coefficient of 1 means that the two random variables are exact copies of one another. They're always identical. Correlation coefficient of 0 means that they're statistically not related at all. And you can actually have a negative correlation coefficient. So a correlation coefficient of -1 means that the two random variables are identical to each other, but one of them just has the opposite sign to the other. So you can see on the previous slide that the expression for covariance contains the mean of the random variables x and y. We know how to calculate the mean. The only quantity that's new is the expected value of the product of x and y. And that can be determined from the joint PDF just by multiplying the joint PDF by x and y and performing the double integral. It also, if you're working with experimental data, can be determined directly from the data. So if we have a data vector x, a data vector y, then the expected value of x times y is just the average of the product of the individual data samples. So let's do an example. In this example, we determine the covariance of x and y if the two random variables have this joint distribution. Now, if you remember from previous modules, this distribution is actually the distribution you get if x and y are independent. And so we would expect the covariance to be 0 for this particular example, and it is, but it's still useful to work through the calculation just so we can see how it works. So the first thing we're going to need to do is determine the mean of x and the mean of y. And to do that, we need to find their marginal distributions. So the marginal distribution of x is just determined by integrating out the y term of the PDF from -infinity to infinity, which for this bounded PDF ends up just being an integral from -2 to 2. And so we get a uniform distribution for along the x-axis from -2 to 2 with a flat height equal to 1/4. We get exactly the same thing for the distribution, or sorry, the marginal distribution for y. And so that means that the mean of x and y is going to be equal to one another. And if we determine that value, the mean is 0, which we would expect because the distribution is symmetric about 0. Now, the only other quantity that we need to determine is the expected value of x times y. We multiply the PDF by x and y, and then we perform our double integration. Our inner integration from -2 to 2 along the x-axis gives us 0 already, so this overall, the overall answer is equal to 0, and so we get a covariance equal to 0, which we would expect because x and y were independent. Now, in most cases in this class, as I mentioned earlier, we consider, when we're talking about jointly distributed random variables, we tend to just sort of restrict our discussion to 2 random variables just because it's a little bit easier to work with within a classroom setting. However, it is important for us to talk about one sort of generalized joint PDF, specifically for the Gaussian case. One, because the Gaussian random variable is so important for electrical engineers, but 2, also because it has a very nice form when we put it in sort of a linear algebra matrix kind of form that's very reminiscent of the structure for the Gaussian PDF for a single random variable. So let's consider a vector x containing n Gaussian random variables. And the joint PDF for this vector of random variables we write as follows. So the argument to the PDF is itself a vector of lowercase x's. And the expression for the PDF itself is as follows. And so we have 1 over the square root of the determinant of c of x, which we call the covariance matrix. And then we have an exponential term, and we have x minus the mean, and then this covariance matrix, which kind of takes the place of the variance term. And so you can see that this structure has a lot of similarities to the form that we're already familiar with. Talking about these other vectors a little bit more closely, mu x is a vector that contains the mean values of all of our random variables. And c of x is something that we call the covariance matrix. And you can see why. It's the random variable vector minus the mean, and then squared, or 1 multiplied by the transpose of the other, and then we take the expected value. So it's very similar to the definition for covariance. And specifically, the element of the covariance matrix so if we look at the element in the covariance matrix that is in row I and column J, that is the covariance between specifically random variable I and random variable J taken from this original vector. So it's a nice compact form for a distribution that we work with really quite a lot. So to get a little bit more familiar with this expression, let's consider an example where where n is equal to 2. So we're using our joint distribution just for 2 random variables. The Gaussian random variables are 0 mean, so that mu x vector is just equal to 0. And then the covariance matrix, and I'm not showing the mean subtraction here because the mean is 0, is just equal to the vector containing the random variables x1 and x2 multiplied by its transpose. And when you take the expected value of each of these terms, on the diagonal you get the variance of the random variables because the random variables are multiplying themselves. And then on the cross terms are equal to the covariance values. And you'll note that the matrix is symmetric around its diagonal. So in the next few slides, I'm going to plot the PDF because we're working with just two random variables. We have the 3D surface that we've been working with in previous modules. So here's the three-dimensional PDF that we get when the covariance between the two Gaussian random variables is 0. So there's no correlation, no statistical relationship between them. And so we have a nice symmetric PDF around the X and Y axis. This is the PDF that results when I increase the covariance between the random variables. I think that this one is equivalent to a correlation coefficient of about 0.8. So we can see that when one random variable is got a negative value, the distribution for the other one tends to concentrate in the negative range as well. When one random variable has a positive value, the distribution for the other one is concentrated in the positive range as well. So we start to see the distribution kind of squishing itself along that x equals y axis, which is a phenomenon that we saw in the distributions that we looked at in the previous modules as well. A common thing for electrical engineers to do is to add or combine two random signals. So let's say we've got a couple of random signals represented by the random variables x and y. We add them together to get the random variable z. And a very normal thing for us to ask is, okay, what's the power, or what's the variance of the summation of our two signals? And so the variance of z is equal to the random variable x minus its mean plus, this should be a capital Y, the random variable y minus its mean squared. If we expand out our brackets, we get this term, which corresponds to just the variance of x. We get this term, which corresponds to the variance of y, and these should be uppercases. This term is the covariance with just a 2 out front. So we've got 2 times the covariance. Now, what we see here is that if the two random variables are uncorrelated, the covariance goes to 0, and the power of z is just equal to the power of x plus the power of y. However, if they are correlated, then the power is actually increased, and that's due to the fact that as the random variables become more similar, they start to add in what we call a coherent fashion, and so the power we get in our summation increases. Sometimes we talk about two random variables being independent, and sometimes we talk about two random variables being uncorrelated. Now, the two concepts are definitely related to each other, but they're not equivalent. They don't mean exactly the same thing. So more specifically, if all random variables that are independent are uncorrelated, however, not all random variables that are uncorrelated are independent. And so what I want to do is expand on the two ideas here a little bit to make that notion a little bit more clear. So let's start with the idea of independence. So if we go right back to our basic probability, we know that two random events A and B are considered independent if the probability of A and B occurring, the probability of their intersection, is just equal to the probability of A times the probability of B. So let's define our random event A as being the random variable x, the value of the random variable x being less than or equal to some lowercase x, and the event B is the random variable y being less than or equal to some lowercase y. And so this probability term then just becomes the expression for the joint CDF. So the probability of x being less than or equal to a value and y being less than or equal to a value is exactly the joint CDF. And if these two terms are independent, then that's just the individual CDF for x multiplied by the individual CDF for y. And if we take the derivative, we get the joint PDF for x and y being equal to the product of their marginals. And this is an expression that I've already given to you in a previous module, but hopefully now you can see a little bit more clearly where it comes from. Going a little bit further with this, we can fairly easily show that all independent random variables must be uncorrelated. So remember, the covariance of x and y is equal to the expected value of x times y, which is just given by this integral. However, if x and y are independent, their joint distribution is just equal to the product of their marginals. And if we replace the joint PDF with the product of the two marginals, we can very easily separate our integrals into a term just for x and a term just for y. But of course, these two individual terms are just equal to the expected value of each. So we end up having the expected value of x times the expected value of y. So if this term is just equal to the expected value of x times the expected value of y, it's equal to that term in the covariance, and then the covariance goes to 0. However, not all uncorrelated random variables are independent. So to show you, let's do another example where we have a random variable w, which is just equal to the difference of two identically distributed but independent random variables, and z is equal to the sum of two identically distributed and independent random variables. Now, since w and z are constructed using the same two random variables, x and y, they're clearly not independent. However, we will show below here that their covariance is actually equal to 0. So covariance of w and z is equal to the expected value of w times z minus the product of their means. The expected value of w times z is just the expected value of x plus y times x minus y, which ends up being, if you expand out the brackets, equal to the expected value of x squared minus the expected value of y squared. However, since x and y are identically distributed, this is equal to 0. Now, we then determine the mean of w, which is the mean of x minus y, which ends up being the mean of x minus the mean of y. But again, because they're identically distributed, these two means are equal, and so this result is equal to 0. And as a result, the overall covariance is equal to 0. So just something to kind of keep in mind. In most practical cases, if your correlation is 0, it means you're dealing with independent things, but just not always. So going back to the sum of two random variables, z is equal to x plus y, where x and y are themselves random variables and they're independent. It's also, in addition to calculating the variance, which we did a couple of slides ago, it's also nice to, in some cases, to be able to determine the overall PDF of the sum of two random variables. And it turns out that it's not that complicated to do this, and we can show how it's done by using moment generating functions. So the moment generating function of z is the expected value of e to the sz. And if we replace z with x plus y, we can divide, we can just turn the summation in the exponent into the product of two exponents and then separate them out using the two different expected value operators, because the two random variables are independent. But these two terms are just equal to the moment generating function of x multiplied by the moment generating function of y. And if we do the inverse transform of this, we end up finding that the PDF of z is equal to the convolution of the PDF of x and the PDF of y. And finally, we'll conclude with a very important concept that engineers use all the time, and that's the central limit theorem. Basically, the central limit theorem says that the sum of any independent random variable can be approximated as Gaussian as long as we have enough random variables in the sum. And this is regardless of the actual distribution of the random variables in the summation. And so this is a really, really important and very useful theorem, because there are many cases in electrical engineering where we have a lot of random quantities being added together, and being able to approximate their sum as Gaussian is often a very simplifying assumption, because we work with Gaussians all the time and the properties of Gaussians are very well known. And so the question typically then arises is, how many random variables do we need in our summation to approach a Gaussian distribution? This varies depending on the distribution. So if the individual random variables in the sum have a smooth distribution, often numbers sort of in the 20 to 30 range will definitely give us a good Gaussian result. But sometimes you can even get away with as low as 5 results. It just depends on the application and how much accuracy you're looking for. I should say here that if you really are concerned about whether or not you've got enough random variables in your summation to approximate it as Gaussian, this is where goodness of fit techniques come in. You would basically just take your summation, apply a goodness of fit test on it to see if it accurately can be represented by a random variable. So to be specific about the theorem, let's say we've got a sum x, which is equal to the summation of n random variables. These do not have to be identically distributed, so they can have their own means and their own variances. So let's let mu1 be the mean for x1, mu_n be the mean for xn. So what we do is we add up all the means, we add up all the variances, and this is where the independence assumption comes in. If they weren't independent, then we would have covariance terms in here as well, as we've seen a couple of slides ago. But then you just add up the means, you add up the variances, and then the overall distribution of the sum is just our standard Gaussian distribution, where the variance is the sum of the variances and the mean are the sum of the means. And so just to conclude this discussion, let's consider the summation of a single random variable, which isn't a summation at all, it's just the single random variable, 2 random variables, and then 10 random variables, and see how Gaussian it starts to look after a while. In this particular example, the individual random variables are independent random variables uniformly distributed between 0 and 1. So this is a histogram of our single random variable, just one of the random variables in our summation. As you can see, it's uniformly distributed between 0 and 1. This is the histogram of the summation of 2 random variables. Now remember, we've learned in this module that if you add 2 random variables together, the PDF that you get is the convolution of their individual PDFs. And so if you convolve 2 rectangles together, you get a triangle. And that's why we see a triangular distribution here after adding just 2 random variables together. This final slide shows what we get after 10 random variables. And after just 10 random variables, we can see we've got something that looks quite Gaussian. Again, if we wanted to be sure, we would do a goodness of fit test. And so this is kind of interesting because 10 random variables isn't really very much to get something that looks fairly Gaussian. It's also kind of an interesting quirk of the convolution property. So if you just keep convolving rectangles together, the more you convolve, the closer you get to a Gaussian shape. So you can think of the Gaussian distribution or the Gaussian shape as sort of the ultimate result of many convolutions, regardless of the shape that you start with.